the reason why we need to know the shapes of molecule is from the shape of molecule and the idea of dipole bonds we talked about from the last lecture, we can classify the whole molecule as something that is polar or nonpolar, not just the bonds in the molecule, but the entire molecule. And when we talk about polar molecules, you can almost imagine them like magnets. When molecules are polar, they are attracted to each other, and just like how magnets are attracted to each other, polar molecules are attracted to each other from their opposite ends. So keep this image in mind when we talk about the polarity of a molecule. In the same way we can describe the dipole of a bond, we can also describe the dipole of the molecule. And first, let's talk about when you can have a non-polar molecule. In the first example, we have H2, Cl2, and O2. All of these molecules are non-polar. Can you think of the reason why? So it turns out the first one is that they contain non-polar bonds. In H2, that bond is non-polar because it is connecting two identical atoms, which means their electronegativities would be the same, so that bond is non-polar. Same thing with Cl2 or O2. Whenever they are exactly the same, their electronegativities will be the same, so they will be nonpolar. So if you have a nonpolar bond, your molecule will be nonpolar also. The second way you can have a nonpolar molecule is when you do have polar bonds, but those bonds cancel each other out. And a prime example is CO2, carbon dioxide. Remember from carbon dioxide, that carbon and that oxygen bond is a polar bond. Which one is more electronegative, the carbon or the oxygen? Right? It was the oxygen. So imagine that bond, the electrons are being quote unquote pulled towards the oxygen. Remember, I say quote unquote because nothing's being pulled physically, but that there are just more electrons on the oxygen side. On the other bond, where is that electron being pulled? In the opposite direction. All right, so now if we combine this idea of bond polarity with the shape of the molecule, we can find out that this will be a nonpolar molecule. And why is that again? Remember, the shape of this molecule would be linear, 180 degrees. So if you are 180 degrees completely opposite of each other and you are pulling with the same strength because both sides are oxygens, they will cancel each other out. So this molecule will be nonpolar. In order to spot these occurrences, always look for some kind of symmetry within the molecule. Here's another instance of symmetry. When you have a tetrahedral shape, those outer atoms are all equally spaced from each other. Because they are all equally spaced from each other and they are the same atoms, they will all cancel each other out. Now, if I were to replace one of them, let's say for example, if I were to replace this with a hydrogen, then it loses symmetry, and then that molecule will be a polar molecule. You can imagine, again using the pulling analogy, this chlorine is pulling it this way and then down, this chlorine is pulling it this way and down, and this chlorine is pulling it to the right and down. They are all pulling down, so overall that molecule will pull down. But in this case, there's another chlorine that's pulling up. So that one up will cancel out with all those small downs. Therefore, this molecule is nonpolar. Let me just clarify what I just said there, because it might sound confusing. Why is that one chlorine up canceling all the chlorines that's pulling down? Well, remember that one chlorine that's pulling up is pulling up straight. So all its energy, quote unquote energy, if this was a tug of war, all of its energy is pulling in the direction of up. Whereas the other chlorine is pulling down, it's pulling down, but they're also pulling out, right? Pulling down at an angle, down to the left, down to the right. Because of that, so all of the components from the chlorines that are pulling down, all three of them, the down components add up together to be the same as one chlorine that's pulling up, because that one chlorine is pulling straight up. Now this is because of something called vectors, and if you stick around to the end, I will talk about vectors and how to do this in a vector sum manner. So I've already hinted when you can have polar molecules. You can have a polar molecule when one end of the molecule is more negatively charged than the other. So in this case, this molecule only has one bond and that bond is polar. If it has only one bond and that bond is polar, then that molecule must also be polar. So more of the electron density is on the chlorine side than it is on the hydrogen side. And as I have alluded in the previous part, the second way you can have a polar molecule is when your polar bonds do not cancel each other out. For example, in this case, water. the oxygen-hydrogen bond is polar, and because of the shape of the molecule, which remember was a bent shape and not a linear shape, if it was a linear, it would cancel. But in this case, it is a bent shape, so this oxygen is pulling this bond this way, and the same oxygen is pulling this bond that way. Notice that they're both pulling upward. Nothing is pulling it down to cancel it. So this overall is being pulled to the top. So we say that the overall, this molecule is a polar molecule with electron density on the top near the oxygen and lacking where it's a partially positive near the bottom with the hydrogens. Again, a molecule is polar because it has an uneven sharing of electrons throughout the molecule. Alright, so let's formalize what we just did. I want to emphasize again how to determine the polarity of a molecule. You need to be able to know the shape of the molecule. And again, in order to know the shape of a molecule, you need to draw the correct Lewis structure. So let's try this with H2CO. This is formaldehyde. We've already seen this molecule. It has 3 electron groups, so the shape will be trigonoplanar. Now let's think about the individual bonds' polarity in this molecule. The carbon-hydrogen bond is nonpolar, so we will ignore it. And the carbon-oxygen bond is polar, and oxygen is more electronegative. So the polarity of this molecule is towards oxygen, and indeed, this is a polar molecule. Another way of thinking about this is if you were having a tug of war where carbon is in a 3-way competition. Carbon has equal strength with hydrogen, so if carbon and hydrogen are pulling and this hydrogen is pulling, it is not moving anywhere. But in this match here, oxygen is stronger than carbon, so oxygen is able to pull it this way. And if it pulls it this way, the whole molecule is being pulled this way. So therefore, if the whole molecule is being pulled in one direction, we call that polar. Again, nothing is really being pulled or moving around, but it's a good analogy to help us understand polarity. All right, from that, let's have a checkpoint. Which of the following molecule is nonpolar? Let's first do some elimination. We know that HF, option A, would be polar because it is a polar bond, and that's only one bond. So HF should be a polar molecule. And we can cancel out option C because that's an ionic bond, so it's not a molecule actually. So our 2 options left is B, NF3, and D, CF4. Again, we need to draw the correct Lewis structure, and that's the correct Lewis structure for NF3, and that's the correct Lewis structure for CF4. From this, we can know the shape, right? The shape of NF3, it has 1, 2, 3, 4. 4 electron group is a tetrahedral arrangement, but it has only 3 atoms connected to it, so it's trigonopyramidal, whereas this one is 4 atoms and 4 electron groups. See how it is important to memorize that chart to know that this is tetrahedral and this is trigonopyramidal. And from this you can see a tetrahedral shape is very symmetrical, whereas a trigonopyramidal is not very symmetrical because it's missing something on the top. Because of this, only this shape will give you something that is nonpolar, because even though there are polar bonds, those polar bonds will all cancel out. Whereas here, they will not all cancel out because there's nothing to counteract the pulling of these 3 since we're missing an atom on the top. So from that analysis, hopefully you came up with the answer that D, CF4 is your nonpolar molecule. Some of you would like to think about molecular polarity as a tug-of-war analogy. For those of you who like to think about it in a more mathematical way, I would now like to show you how. So I have alluded to it before, but I haven't stated out explicitly yet. But molecular polarity is actually a net polarity. And what does net mean? That means you have to add it up. It's the net polarity of all of the individual bond polarities in the molecule. Okay, so again, the overall polarity of the molecule is the sum of all the bond polarities in the molecule. Yeah, so if you just add up all the individual bond polarities, you will have a polarity of the molecule itself. All right, so let's take the simple example of CO2 to illustrate this point. Remember that CO2 is a linear molecule, and in the CO2 molecule, there are 2 bonds
two CO bonds, and each of those CO bonds are polar bonds, right? So let's just assign a value to this polarity. I'm just make up a number. Let's say 5. If it's going to the right as positive 5, then going to the left would be opposite, right? Negative 5. So again, we're trying to think of this in a mathematical way, so we need these positives and these negatives. Let's add these sums up together. What's 5 plus negative 5? 0. So the net polarity of CO2 is 0, therefore we call it nonpolar. Another way of thinking about that graphically is, let's go, you start at 0, okay? You add 1 bond first, so from 0 you go to negative 5. You're there, right? So that's 1 bond. Now let's add the second bond. The second bond is positive 5, so you go in the opposite direction on this graph. So from here, you go back to here, 5 units, right? So where do you end up? You end up at 0. Therefore, the sum is 0. So that's graphically. I know that was pretty simple. We didn't need to see that graphically, but this is important for my next example. Now let's imagine that you didn't know CO2 was linear. Let's imagine you think CO2 was bent. If CO2 was bent, it still has 2 polar bonds, and those polar bonds still have the same value, right? I'm not going to put positive or negative in this side because it's not on the x-axis, so we don't know what the size is. But I can draw it out. It's not going to be to scale. So these are called vectors, basically. So you can add these vectors up. But it's hard to add a vector up if it's not exactly on an x or y axis. So remember in your math class, and maybe I think this is geometry class, or algebra, you can break up your vectors to its x and y component. So let's do the left hand first. If you're going down that way, well, if you break that up, its x component goes that much, and its y component goes down this much. Let's just call it x and y. Let's just call this negative x, and then this is negative y because you've gone down, right? So this is negative x because you've gone to the left. This is negative y because you've gone down. Okay, so that was this bond. Now let's do the bond on the right. So remember, the bond on the right goes down and to the right. So you can also break it up into its x and y component. It goes over to the right, and it goes down until it is at the same point, right? Okay. Okay, so in terms of going to the right, how much did it go to the right? It should go to the right exactly positive x, right? So it goes plus x. And then where did it go? It goes down, but how much? It goes down to about the same y value, right? Because it's the same y value, so it went down negative y. Okay, now let's sum up those vectors. You got negative x and positive x. What happens to them? They cancel out. That's negative x plus x is 0. What else do you have? You have negative y minus y, or negative y plus negative y, which is negative 2y. Okay, so is this 0? No, it is not 0. Okay, so mathematically, if you add all the bonds together and they add up to 0, then they are nonpolar. If you add them all up and they are a number that is non-zero, then it is a polar molecule by definition. So if you like that math way, you can think about it in that mathematical way. If you like it, the tug-of-war analogy, then you can use the tug-of-war analogy.